blessing all the trap niggas. God blessing all the trap niggas. When you wake up before you brush your teeth, you grab your scrap nigga. All the time.
So now let's talk about hybridization. And this is the idea that atomic orbitals fuse to form newly hybridized orbitals, and this in turn influences molecular geometry and bonding properties. And so in order to explore this idea further, I'm going to utilize 3 types of hydrocarbon compounds to illustrate sp3, sp2, and sp hybridization. But before I get started with that, let me write out the electronic configuration of carbon, which is 1s2, 2s2, 2p2, since it has 6 electrons in total. So if you just look at this simple carbon electron configuration, you see that carbon has 2 unpaired electrons in the outermost p orbital. So theoretically, this means that it will only form 2 bonds, but that's definitely not the case, right? We've seen methane, which is 4 bonds to hydrogens. There's a lot of different kind of hydrocarbons. So what's happening there is that if I write out energy is increasing up here, we're not showing the 1s2 orbital because it's the innermost orbital and it's not going to be affected by hybridization. But in the ground state configuration, we have 1s2, 2s2, 2p2 due to Hund's rule. But then in the excited state, one of these electrons from the s orbital is going to get promoted because it's in an excited state. But at this point, we only have these 3 in the higher electronic energy shell, but we don't want them to be just higher in energy. So we create these sp hybrid orbitals, which are lower in energy, but also able to bond with other atoms. So we're going to move this 1s orbital and 1p orbital and create these sp hybrid orbitals, which are lower in energy than this 2p orbitals that we started out with. So in this case, now we have 4 areas in which we can make bonds. So if we look at carbon dioxide, for example, this is a linear molecule and this is 180 degrees. In order for carbon to make 4 bonds in total, 2 with this oxygen and 2 with this oxygen, based on the VSEPR and the Lewis structures that we talked about before, now it can have 4 areas in which it can make bonds. So it makes sense that it's going to be linear. So now let's move on to sp2. We start out with the same exact ground state. We have 2s2, 2p2. For the excited state, let's promote an electron again. But in this case, for sp2, we're going to mix 1s orbital and 2p orbitals. So we're going to mix this one and 2 of these guys and create these sp2 hybrid orbitals, which again are lower in energy than the original 2p orbital. And we have 1 unhybridized p orbital that remains. So in this case, let's look at C2H4 as an example, where in this case we have this carbon that's in a trigonal planar configuration, 120 degrees. And so in order for this carbon to make 3 bonds with other atoms, it's going to have 3 areas in which they can attach. And so 1 here, 1 here, and 1 here. And then it also has 1 unhybridized p orbital remaining. And so the configuration is going to be trigonal planar. Finally, looking at sp3, we start out with the ground state, we promote an electron to the higher energy excited state, and then in the hybridized state we have 4 areas in which we have sp3 hybrid orbitals. So again, lower in energy than the 2p orbital, and now it has 4 areas in which it can make bonds. And so an example of this is methane. Like so, this is 109.5 degrees that we talked about in VSEPR. And as you can see, each of these hydrogen atoms could have come in to form bonds. So although I gave examples using carbon, which is one of the most versatile atoms, you can also do this for any other VSEPR molecule that you may have seen. So for example, for trigonal planar, A typical one that you see is BF3. You can do this exact same thing with this boron atom. Start out with its ground state, move an electron up to an excited state, and then based upon the hybridization, move one s orbital and two p orbitals to create an inner hybrid orbital, which is lower in energy than the original 2p, but it allows you to make bonds with other atoms. And so now we'll talk about Sp3d and Sp3d2 hybridization. So here's a pretty good table to summarize the hybridization that we went over. Sp, Sp2, Sp3, the different shapes, the different number of atoms involved, as well as the different bonding. So now let me go over Sp3d as well as Sp3d2 hybridization. So this is Sp3d hybridization. So as you can see, it's going to involve one s orbital, three p orbitals, and finally one d orbital. So in this case, the example is chlorine with 3 fluorine atoms attached, as well as 2 lone pairs right here. So it has 5 as the steric number. And now let's look at the ground state of the chlorine. So it has 1, 2, 3, 4, 5, 6, 7 electrons for the 3s and the 3p orbitals. Remember, there's also the 1s2 and the 2s2 that's not being shown here. And then in the excited state, we're going to promote one electron into the d orbital from this p orbital. So this might be a little hard to see, but we're basically promoting this into the d orbital so that now we're able to form 3 bonds with the fluorine. These boxes right here are indicating the lone pairs that are on the central chlorine atom. But basically the fluorine can come in and make bonds here, here, and here, thanks to the hybridization that we did. Finally, for Sp3d2, an example of this is PF6, steric number 6, so it's octahedral. The phosphorus in the ground state has 1, 2, 3, 4, 5, 6 electrons, including the s and the p orbital. And so we're going to promote an electron for the excited state, 2 of these into the d orbital. But one comes from this p orbital, and another comes from the s orbital. The reason for this is because we need 6 areas in which the fluorine can come in. And so for the Sp3d2 hybridization, we're promoting an electron from the s orbital, the p, and the d, and we're mixing them all together in this hybrid orbital where we can have fluorine electrons come in and make bonds here, 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 and here, which is 6 spots. So we get Sp3d2 for PF6. So this was a little different from all the other examples that I did due to the lone pairs that existed, but otherwise it's exactly the same as the Sp, Sp2, and Sp3 hybridization that I showed you guys before.
Sold over $1 million dimes hanging in the cut. Sold over $1 million dimes, don't give a fuck. What? When you wake up before you brush